An important characteristic or behavior of sound as it travels through a medium is that as the distance increases, its intensity and amplitude also decreases, and thus it becomes attenuated. So as the wave travels through the medium coming from the source, as you go further and further from the source, the intensity and the amplitude decreases and it becomes attenuated. This is an important property that we need to know, especially when we do medical ultrasound, because we have to realize that the deeper we go and the deeper we interrogate using the ultrasound, the weaker the signals become. So the deeper the wave travels in the body, the weaker it becomes. And there is a measure of an attenuation of the waveform. So if you're doing ultrasound on deeper structures of the body, you will have to realize that as the ultrasound is transmitted by the transducer, there is a certain distance that it has to travel, and there is a second distance that the echo will need to travel in order for it to be detected by the transducer. So the deeper the structure is, the weaker the echo amplitude becomes. And this is very important because we now need to adjust certain settings in the ultrasound machine in order to compensate for this attenuation and for this decrease in echo amplitude. And we will learn more about this in the following lecture on knobology, but I am introducing to you the concepts so that you will know that this particular property and behavior of sound through tissue is an ever-present phenomenon that needs to be compensated for. Now, what causes these attenuations? Attenuations can happen because of reflection and scattering as the sound waves hit the different media or the different molecules of the medium. There's going to be reflections and scattering, and it's not going to travel really in a straight line, but it's going to hit molecules and travel to another direction, which makes it lose energy, and this loss of energy will result in a decrease in amplitude. So that is one of the attenuation mechanisms, but this is a minor effect because most of the attenuation mechanisms occur because of absorption effects. And absorption effects, being a major attenuation mechanism, is also affected by the kind of frequency. Absorption is frequency dependent. Higher frequency sound will tend to be absorbed quicker than lower frequency sound. So that means that lower frequency sound can travel much further than higher frequency sound because the attenuation is much lower with lower frequencies than with higher frequencies. Therefore, where penetration is needed, low frequency probes are usually required. And we will talk about these transducers later on when we go into transducer theory. So attenuation, or the decrease in ultrasound amplitude, increases with frequency. Now we now know that sound used for medical diagnostics is above 1 megahertz. And sound above 1 megahertz cannot, due to reflections, enter air. So again, for tissue reflections or tissue interactions, if there is air within the tissue, the sound being a higher frequency is already being attenuated by the distance, and then as it enters an air gap, it cannot be transmitted further on after the air gap because the attenuation happens here in this air gap largely because of reflections and absorptions. So that is why in ultrasound, it is very important that we try to insonate the areas of the body which have less gas. And if there is gas in that area, we have to prepare the patient to remove the gas, from that area. So that is why if you're going to do abdominal ultrasound, we don't want to have the patient fed a few hours before the procedure, because in feeding, the patient will be swallowing a lot of air, and a lot of air is going to be seen in the intestines, and this intestinal air is going to block the transmission of sound because of this air gap. To repeat, the attenuation results from absorption or the conversion of sound energy into another form of energy, which is usually heat. So higher frequencies undergo greater absorption. Now, this is important later on when we talk about the ultrasound safety, because although we know, and although it is generally known that ultrasound is generally safe, we know that the absorption mechanism of attenuation will convert mechanical energy or the vibrations into heat energy, and that results in the attenuation. So ultrasound produces heat energy. And this phenomenon is actually being used by certain devices for sterilization of instruments. Instruments can be sterilized using ultrasound because the heat energy that is produced can be harmful to the bacteria. And so it is also important for us to know that prolonged insonation of a certain location in the body may result in a temperature increase of that particular location if you keep the probe there long enough. So we will be talking later on in another module about ultrasound safety, and you will be introduced to the principle of ALARA, which is as low as reasonably allowed. And that is the basic principle of ultrasound safety, where we should only use ultrasound for its intended purpose and not for anything else, because it is a form of energy that can and does have certain harmful effects if not watched out for. Okay? Now, the minor forms of attenuation are reflection and scattering, and sound is reflected when it reaches a boundary between two dissimilar media, and this is what we call the acoustic interface. So if you have blood and fat, or fat and muscle, this boundary between them, you will have an acoustic interface, and you will have this reflection that we will be able to see in the ultrasound machine. Now, scattering occurs when an ultrasound wave strikes boundaries between two media that have irregularities, and the wave is scattered in different directions. Therefore, the echo of the wave that hits that particle bounces off in another direction, and it is not reflected back to the transducer. And so the transducer will detect it as a weaker signal compared to how it was transmitted. Now, since attenuation is a predictable mechanism, it is compensated for by a time gain compensation. And fine-tuning of this gain compensation is typically done using a number of slide switches or slide potentiometers. And because of that, with this predictable decrease in signals along the depth or along the distance traveled by that sound, we can adjust the time gain compensation to increase the sensitivity of the probe to the smaller amplitude waves, such that we will have a pretty much uniform homogeneous wave that is detected by the transducer and then worked on by the CPU. And so if you do not have this time gain compensation, you will see that closest to the probe, it's very, very clear, it's very, very visible, but farthest from the probe, it's going to be very dark and maybe the resolution is not going to be very good. But with the time gain compensation, you can adjust certain switches and certain knobs in the ultrasound so that the weaker signals will be strengthened, will be picked up more, and the signals will then become equal to the signals obtained from the echoes come closer to the ultrasound probe. And then you will have a more homogeneous image. So more of this in the lecture on knobology following this module. So we talked about the pressure, and now we will be talking about the transducer, which job is to produce the ultrasound so that it will be transmitted to the organ of interest. And then it also picks up the echoes of the sound so that it will then be analyzed by the CPU. The analysis of the CPU will then move the data to the monitor for visualization. So basic transducer theory is that the transducer produces a beam which is directs the acoustic energy produced by a transducer. This beam is produced by a transducer. This transducer is a device capable of converting energy from one form to the other. In this case, electrical energy to mechanical energy and vice versa. In ultrasound, the term transducer is used to refer to the crystal and the surrounding housing. There is a housing or a probe, if you will, that houses a crystal, a live electrode crystal element that works by vibrating, and this crystal that vibrates is the one that produces the particle vibrations to make ultrasound. So there are different kinds of transducers. There are mechanical transducers and there are electronic transducers. At this present day and age, we rarely see now mechanical transducers. This was the first generation ultrasound probes. Now we will almost always see electronic transducers with the elements arranged in an array, and there are multi-element electronic transducers that allow it to operate at different frequencies. So this is the mechanical transducer. You will see here that it emits a wave, and the movement, mechanical movement of the array allows it to sweep back and forth so that there will be a accumulation or a collection of ultrasound reflections, which is then collected by the central processing unit and analyzed and brought out to the display monitor. But the electronic array transducer actually has multiple beams being transmitted out. So it's not a mechanical event now transmitting beams at the different angles, but we now have multiple beams coming out from the array. There is an array of crystals that will allow the beam to be propagated or to be transmitted away from the transducer. And there are different types of array transducers. You will have here a linear array, which means that the beams are transmitted longitudinally in a flat manner such that the footprint of the ultrasound transducer or probe is nearly the same as the beam being transmitted. The curvilinear array has a convex surface that allows a diffusion outwards of the beam such that the beam and the image that can be picked up is much greater than the footprint of the transducer. So how does this crystal produce sound? That is explained by the principle of piezoelectricity. Piezoelectric crystals are the primary components of an ultrasound transducer, and they're made of lead zirconate titanate material, and they convert electrical energy into acoustic energy during transmission, and vice versa, acoustic energy into electrical during reception. So if this is a crystal and you have electrons traveling through it, if the electrical voltage is supplied and you have electrons traveling through this crystal will then start to vibrate. So there is a conversion of electrical energy into mechanical energy. This vibration at a particular frequency will create the areas of compression and rarefaction, and thus result in ultrasound propagation. It also works the other way. If sound waves hit the crystal and these propagated sound waves of compression and rarefaction makes this crystal vibrate, the vibration of the crystals will induce movement of electrons, and thus mechanical energy is converted into electrical energy, which is then interpreted by the CPU. And then there's another conversion of electrical energy into light energy so that it can then be seen now onto display monitors. So the piezoelectric effect is the effect caused by crystals changing shape when in an electrical field or when mechanically stressed, so that an electrical impulse can generate a sound wave or a sound wave can generate an